Okay, let's begin. We are going to cover something entirely new today, and I'm pretty excited about it. You may be excited about it? Because I don't get to teach it often. It's not like calculus where hey kids, you know what a tangent line is? Like I've said that thousands of times. Right. I haven't gotten a chance to say this thousands of times to a class, though. Markov chains. They're really cool. I didn't learn about them when I had a probability class, and you guys are lucky to learn about these after the fact. But they're really cool, and they're very applicable, and we'll talk about some of those. First, maybe I should define, I mean, we've been using these, but just to make sure that we're clear. Talk about a random variable. So this is a function that assigns a numerical value to each sample point in a sample space. So basically, this is just a function that allows us to go from a qualitative state of affairs to a quantitative state of one, because we're doing math. So, for example, x is a variable where p of x equals k is given by nck, e to the k, q to the n minus k. Then we can call x is a binomial random variable. So random variables are really neat. The binomial random variable is something that's called a discrete random variable. There are also continuous random variables, but we don't deal with those in finite probability. So that's an example of a random variable. Here's another example of a random variable. You flip a coin twice. So basically once you say, let a variable be something, let x equal the number of heads that appear. That pretty much assigns a number to every event. So in your sample space, it will have a bunch of sample points. Namely, you could get two heads, you could get a head and a tail, you could get a tail and a head, or you could get two tails. There are four things, but these aren't numbers. Basically what I did by defining this x is I was able to connect this to a number. Namely, HH would be connected to 2, HT would be connected to 1, TH would also be connected to 1, and TT would be connected to 0. So me asking, what is the probability that I will only get 1 heads is the same as me asking, what is the probability that this function will output the number 1? Okay? So it's just me being able to use numbers to describe situations in a sample space. And I'm not going to really talk too much more about this, but random variables are very important. So once you start to want to do calculus with probability, this is how you'd actually do it. You actually define functions like this, and then you know how to do calculus with functions, so now you can do calculus with probability. Anything we can do with functions, we can do with probability just by defining random variables. So that's an important thing. Now, to the titular definition. What is a Markov chain? A Markov chain is a sequence of random variables. x1, x2, x3. You can have n of them, and can be very large, and could be infinite, but we're only dealing with the finite case, that have possible output values 1, 2, all the way up to, usually called it S, because the output values are called states. So we can say we have a list of random variables. We have a list of functions that is describing some sort of probability sample space, and they have a certain number of outputs that they can give you, 1, 2, up to S. And we can say when the function outputs that value, it is in a certain state. So I can talk about the random variable x2, it is in state 3. Or the random variable x3 is in state 1, or so on and so forth. Such that the following holds. There are two properties that makes this kind of, so a sequence is just a list in a definite order, so we have a list of random variables, and they can output values between 1 and S. We call these values states of the random variables. The random variables, how do you know it forms a Markov chain, is if it fulfills two properties. Namely, the first one is the probability that your xn plus 1 is going to be equal to some number j, given that your xn was equal to some other number I. So this is saying like, okay, if your x1 is this, what is the probability that your x2 is that? Or if your x5 is this, what is the probability that your x6 is that, right? So the probability of you knowing one state, the state of one random variable, do you know the state of the next random variable? What is the probability of that? And it works out in the following way. Markov chains forget the past. They only count on the present. So if someone were to tell me what all the previous guys were doing, all the way down to the very first guy, the Markov chain is going to ignore all of this information and it's just going to say, the only thing that matters for this is what happened right before. Right? I don't care about what was happening into the list up until this point. I just want to know what's going on now, and I can tell you what's going on in the future. You telling me all this information doesn't actually matter to me. Right? So to figure out what the next guy is doing, I just have to know what the previous guy is doing. And yes, we know you should remember your history, but there are certain contexts where we don't actually care. In lots of science, physics especially, for example, you won't really care. If I know that there's a particle right here in this position moving in that direction at this velocity, I don't care how the particle got there, right? It doesn't matter how it got there. If I want to predict what it's going to do next, I don't know why. Well, why was it here? Why wasn't it at home? Right? I don't care. Like the particle is there now. I can use what it's doing now to predict what it's going to do before. I don't need to know what it was doing 10 years ago, right? So Markov chains have that kind of property. We forget the past. Pretty much we predict the future based on the present. And two, it is time insensitive. This means that the jump from the xnth position to the nth position to the n plus first position is independent of n. And is constant. So an example here, this is telling you that, okay, what is the probability that if x6 was 1, that x7 is going to be 2? Well, that's the same as you asking, what is the probability that if x3 was 1, x4 is 2? That to me is exactly the same as the probability that if x sub 1000 is 1, what is the probability that x1001 is going to be 2? Once something is one step apart, I don't care what point in the list I am, the chances of going from the state of 1 to the state of 2 is always going to be the same once I'm making one step. It doesn't matter where in the list I'm making the step. That's another property of Markov chains. And that's it, that defines a Markov chain. Think of any property where the past doesn't matter, you only need the present to predict the next phase of the future. And to jump from a certain situation to one other situation, it doesn't matter at what point in time this actually occurred, the probability is going to be the same. This is called a Markov chain. Now, I do get that that's a little bit abstract, so let's actually talk about this with an example. And as time goes on, of course, I'll give you more examples. We'll do some cool things with Markov chains. Here's an example. And I'm going to teach you a lot about Markov chains using this example. Exploratory. I don't know if that's my example. So here's a situation that you can describe with a Markov chain. And I'm going to show you why you wouldn't call it a chain in the first place. Insert machine in a factory. So here's what I'm telling you about the machine in the factory. If it is working one day, there's a 90% chance it will be working the next. If it is broken one day, there's an 80% chance it will be fixed and working the next day. So we have this kind of machine, right? We've had the machine a long time, we kind of know how it is, right? So 5 o'clock every day, you're locking up, guy checks the machine, everything operational, okay, we're good. 90% of the time he does that, the next morning you open the factory and you start up that machine, it will be in perfect working condition, right? 90% of the time, everything's going to be fine, assuming it was fine the previous day. However, every now and then, someone checks the machine and it's not working. Right? So they'll they'll put up a call to facilities, hey, the damn thing's broken again, blah, blah, blah. 80% of the time, facilities responds within a day and fixes the machine, right? So that's the situation. Right? So if it's working, there's a 90% chance it will continue to work the next day. If it's broken, you can get it fixed. There's an 80% chance it will be fixed by the next day. And there's a 99% chance it will be working upon installation. Right, so usually if you order one of these new machines, the guy who installs it knows what he's doing. 99% of the time he comes, he sets up the machine, and it'll be functional. Okay? Now once you have that machine up and running, if it's working at the end of one day, 90% chance it's working the next. And if it's not working at the end of one day, 80% chance by the time you come in the next day it's going to be fixed. It turns out that that describes a Markov chain. I want you to notice that if you wanted to find the probability that this machine is going to be broken tomorrow, you don't actually need to know what the machine was doing last week. You don't need to know what the machine was doing 3 days ago. You just need to know what was the machine doing yesterday, today. How is it today? If you tell me about today, I can tell you about tomorrow. If you tell me that it is working today, I can tell you, oh, there's a 90% chance it's going to be working tomorrow. tomorrow. Tell me that it's broken today, there's an 80% chance it's going to be fixed tomorrow. You tell me what happened 2 days ago, 3 days ago, a week ago, a month ago. I don't actually care. At least not yet. So this actually defines a Markov chain. How would we actually create a chain? Well, we would create a random variable. So let x n equals the state on day n. So let's do. So I'm going to have a random variable where here's how I'm going to do the output. 1 means it's working. 2 means not working. So here I've just defined 2 states. I'm going to create a list of variables that they're going to output either 1 or 2. So if I go on day 3 and it's not working, that means that x3 outputted the value 2. Right? So 1 means working, 2 means not working. So I can create a list of random variables that is pretty much going to track the functional state of this machine on day n after installation, let's say after installation, to start at some point. So, let's actually find some probabilities here. And let me do a shorthand notation. P of ij. Basically what this is going to be shorthand for is P that xn plus 1 is going to be j, given that xn was I. Right? So this is the probability of moving from a state I to a state j. So given that we were in state I, what is the probability that we will be in state j? Okay. So these guys are called, because they kind of tell you how you transition from one state to another, they're called transition probabilities. And you will notice that we have 4 such probabilities here. What are the probabilities? Well, here's one probability. I could be working one day and then working the next. What is that probability? 90%. However, there is also a chance that I was working today, but tomorrow I am not working. Let's actually put that down. Okay, so this means you're moving in this direction. Don't forget the notation. You actually move from right to left. So you started in position 1, you transitioned to position 2. Okay, so here I was working on day 1. I am also working on day 2 because one is working. I was working on day 1. I am not working on day 2. What is that probability? Come again?
Just the inverse.
Right? There's a 90% chance that I would continue to be working, so there must be a 10% chance that I'm no longer working. Okay, let's find another one. What if I was not working? What is the probability that I will be working the next day? There's an 80% chance. Okay, so what if I'm not working? What is the chance that I would be working the next day? Not working the next day.
20%.
Notice anything? First of all, there's no other state, right? It looks like a matrix. Yeah. You saw that mischievous look on Jhevon's face, was like, I know this kid is up to something. Why is he listing them out in a rectangle? Like, why would he do that? Right? Why did he have a problem writing the 2-1 here and insisted to write it there? It looks exactly like a matrix. Me jumping from one state to another state, I can think of these as matrices. We can put these in a matrix. It's called a transition matrix. Because it pretty much tells you the probability of transitioning from one state to another. So, in this matrix, I can put, of course, the locations are going to be first row, first column, first row, second column, second row, first column, second row, second column, and of course the numbers are 0.9, 0.8, 0.1, and 0.2. This is called a transition matrix. Sometimes people set them up based on the yes, I did actually set it up the other way. IJ for IJ. So it doesn't actually matter, but I actually want this to coincide with your textbook, so let's put this in the other direction. Because I believe your textbook looks at it this way, because people normally read from left to right. So go from state 1 to state 1, that's still 90. State 1 to state 2, put the 0.1 here, and put the 0.8 here. It'll work either way, but your textbook does it this way. So it was working, it's not working. That's a 10% chance. It was not working, it will be working. That's a 0.8% chance. Because your book says something about the rows, I want to make sure that I'm saying the exact same statement. I want you to notice that the rows sum to 1. So that's how that's one way how you know that you're setting up the matrix in the correct way. Either the rows or the columns should be adding up to 1, but in your textbook they let the rows add up to 1. So what you think of the rows as, this is the current state. Right? So you could actually currently be in state 1 or state 2, and across the columns you think of it as the future states. You can be in state 1 or state 2. So the entry in 1.1 says, I was in state 1 and I moved and I remained in state 1. There's a 90% chance of that. If I was in state 1 and I moved to state 2, there's a 10% chance of that. I was in state 2 and I moved to state 1, there's an 80% chance of that. I'm in state 2 and I remain in state 2, there's a 20% chance of that. So I can literally write down this matrix and it would represent a transition probability. And normally, I believe your book calls this big P. So this we call big P, or transition matrix. So given a Markov chain column, once you realize that you can talk about a sequence of events and it has the two properties that I mentioned, you can create a matrix that literally describes how you can change between states. And of course, the number of rows and columns depends on how many states there are. there were two states in this situation. They were not working, so I end up with a 2 by 2 matrix. If there were 3 possible states, I would end up with a 3 by 3 matrix, and so on and so forth. So that's called a transition matrix. There's another way to look at this. We can express this in graph form. And by graph, I mean the kind of graphs that you would learn about in graph theory. Just nodes connected with edges. As called a transition diagram. Or graph. And I could do the following. So I have two states. The states are represented by nodes. So I have 1, and I also have another state called this state 2. Okay. And then I can actually draw a picture that would describe how I can jump from one guy to the other. So for example, if I am in state 1, I know it's possible for me to jump to state 2, and I write an arrow to represent that. It's possible for me to move from state 1 to state 2, and I can write the probability on that arm. If I am working, the probability that I'm not working the next day is going to be 10%, right? Also, you would notice that 1 actually maps to itself, so you can create a loop. So there's a probability that I'm working one day and I'm also working the next day, so I can just write that this loops to itself with a probability of 0.9. It's also possible that if I'm in state 2, I can jump to state 1. So if I'm not working, there's a probability that I will be working in the future. That's actually 80%. However, 2 also loops back to itself. It's possible that if on one round I'm not working, that in the next round I will continue to not be working. Though that probability though is 0.2. And this is why it's called a Markov chain. You can literally build a chain, connect these states with all these edges that you're kind of describing how can you travel between states. Not all the time can all states travel between each other. It depends on the situation. But for this one, it has a very nice transition diagram. So it's very nice and symmetric. 1 can travel to itself. 1 can also travel to 2. 2 can travel to itself. 2 can also travel to 1. And you list the special probabilities here. I want you to also notice that the rows sum to 1, that's because there's the sum of all probabilities, because if you're in state 1, you'll either stay there or you jump to somewhere else. That's all probabilities for if you start out in state 1, so the sum must equal to 1 by our axioms. Similarly here, when you draw a proper transition diagram, that the sum of the arrows leaving a point is 1. So equivalently, that's going to be happening. So notice that if I'm at the point 1, this arrow is leaving it, that's 0.1. This arrow is also leaving it, that's 0.9. They add up to 1. Notice that what's going into 1 is actually larger than 1, but I don't care. We just care that the things emanating from the point, they all add up to 1. Because that's all the possibilities of you being at that point and jumping to some other point. So that's called a transition diagram, and it gives you a chain. You can connect all these guys with edges. It's called a Markov chain. There is another important matrix, since we're here with matrices. So there's the transition matrix. That's the matrix that tells you how do you jump from one state to another, and what is the probability of you jumping from one state to another. Another important matrix it's called the I'm gonna give you first the initial state matrix, and there's a state matrix in general, but let's talk about the initial state matrix first. This is basically a matrix that describes the initial state, right? So on day one, what situation were you in? Or what is the probability of you being in a certain situation on day one? So these guys are usually called S. The initial one I will call S1 because this is saying on day one. On time one, what are you? This will be a row matrix. And in each, I would put a probability. So this is probability you start in state one. And this is the probability you start in state two. For this particular example, what are these probabilities? Yeah.
99, 1.99, and 0.01.
This is the initial state of your system, of your Markov chain. There's a 99% chance that you will be in position 1 in the beginning. There's only a 1% chance that you'll be in position 2. Given that you start off there, you can use this chain to kind of jump from one state to another and calculate probabilities. Now, let's talk about the important questions. Why do we care? Why this important questions? Here's one question that we want to know. What is the state on day n? Some point in the future, what is the state? Okay? I don't care about, yes, I can see it's working today, and yes, I know the chance of tomorrow, but what I really care about is the inspector is coming next month to inspect the factory. I want all our machines up and running. I want us to look good. What is the chances that we'll look good and it's not going to mess up, Johnson? Right? So, what is the probability it's going to be working on day n? Yes, I know it's working today. Will it be working 32 days from now? Right? That's the kind of question that we want to answer. That's the point of probability. You want to predict the future, kind of, right? You want to be able to do it very long in advance. Another thing that you could ask for is what is the expected value of our variables? Can I expect a certain state to show up at some point in the future? 3. And this is also a nice one which we're not really going to talk about 2 a lot, but we'll talk about 1 and 3 a lot. Another thing we can talk about is what is the long-term behavior? Right? Meaning, as your time n is going off to infinity, right? For the foreseeable future, what do you think our situation is going to be? What are the chances we're in this situation versus another for the foreseeable future, right? These are questions we can ask. These are the important questions to ask. These are the ones that we want the probability to actually help us out with. So let's actually try to figure out how that will actually work. Let me recopy this diagram. Let's ask this question. So we have this, that's 1, 2, root to itself, root to that. Boom, 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 boom. This is state 2, this is state 1. Probability of 90, probability of 10, probability of 2, probability of 80% respectively. And so I can ask the question. It's working today. I know that there's a 90% chance it's going to be working tomorrow. What is the probability it is working 3 days from now? Or let's do 2 days just. So So I don't want to know about tomorrow. I want to know about the next day. I mean, we can even do 3 days from now, just to make it a little bit interesting. Okay, so how would you actually figure that out? Basically, what you want to actually do is you want to, one way you can do it, we're going to find a better way right away. One way is to look at the chain. Start at 1. Find all the ways to get back to 1 in 3 steps. Right? That's 3 days from now. Okay. So if I start at a functional state, what are all the ways that I can remain in that state? Well, one way is to just keep looping around. Right? 1, it's working the next day, it's working the next day, it's working the next day. So I can literally, one way is to go from 1 to 1 to 1. That's a way to start at 1 and end at 1, taking 3 steps. Right? What is the probability of that? Well, it's 0.9 times 0.9 times 0.9. Right? So it's working this day and the next and the next, and here we're not saying it's independent because they're actually not independent. Markov chains are dependent. We'll talk about that later. But we're using the conditional probability. Given that it's working today, what's the probability it's working the next day? I'm using the P of A given B is P of A and B over P of B. So the P of A and B means P of B times the conditional. So we have the multiplication here. That's one way. Or, what's another way? What's another way I can start at 1 and stay at 1 by making 3 steps? Yeah?
1, 2, 1.
You go 1, 2, 1. Is that possible? Well, we wanted 3 steps. 1, 2, 1 and stay at 1?
Yeah.
Okay, so the chances of that are, well, there is a 0.1 chance that we'll jump to 2, and then there's a 0.8 chance that I'll jump back to 1, and then there's going to be a 0.9 chance that I stay at 1. Or, yeah,
1, 1, 2, 1.
I can stay at 1 step,
Yeah.
2 steps,
Or no, you
what that'll be?
yeah, the third step is to go.
1,
Yeah.
2, 3.
Yeah.
So I stay at 1, jump to 2, jump back to 1. So if I am at 1, what is the probability that I will jump to 1? Well, that's 0.9. What's the probability that I will jump from 1 to 2? Well, that's 0.1. What is the probability that I will jump from 2 back to 1? That's 0.8. Is there another way?
Yeah. Would it be 1, 2, 2, 1?
1, 2, 2, 1. So I jump from 1 to 2, there's a 0.1. I stay at 2, that's probability of 0.2. And then I jump back to 1, probability of 0.8. Any other situations? Think of any other situation?
No.
That's it. So it will be this plus that. Now, clearly as you can see, we only have 2 states and it was highly annoying just figuring out 3 days in the future. How am I going to find out a week in the future, a month in the future? Well, the answer is we're not going to do that. Right? Here is something else that you're going to see. Cool. And consider this. Consider. if I were to take S times P? Matrix multiplication. Okay, so our S was what? Our S was 0.99 times, this was 0.01 multiplied by P. What was P again? This was 0.9, 0.1, 0.8, 0.2. Is that it? Was that it?
Yes.
Multiply that, what would we get? Well, we would have 0.99 times 0.9 plus 0.01 times 0.8, and we would have 0.99 times 0.1 plus 0.01 times 0.2. I would get another row matrix. Reminds me that we're forgetting something there, but we'll fix it here. What is this? Calculated equivalent. Do this. What do you get here?
0.899.
0.899.
Yeah.
What do you get over here?
Oh, I just did them all, so 0.99.
It's gonna be annoying doing 3. Should have stuck with 2.
Oh, the first one would be 0.891. And the second part would be 0.008.
008.
Wait. I'm sorry.
No, you were right on the
I'm
first
done.
one.
I'm done.
It's 0.899.
I'm done. Excuse myself.
Too early. It's too early for matrix multiplication. Let's do this afternoon. What is this?
101.
101. Okay. Let's take a breather here first. Interpret these numbers. What do you think those numbers are? Yeah.
Is that the state of day 2? Or the probability?
Right. This is the probability you're in state 1 on day 2. How do you know? Well, Bayes' formula actually just happened, right? If you notice what happens, this is the probability that we're functional given that we were functional multiplied plus the probability that we're going to be not functional given that we're functional. If you write this out, you'll see that this is Bayes' formula. This is going to be the probability that we're in state 1 given that we're in state 1 times the probability that we were in state 1, which is that, or what is the probability that we're going to be in state 1 if we came from state 2 times the probability of being in state 2. That's actually Bayes' formula that just happened in this. Right? So you realize the matrix multiplication actually falls right in line with Bayes' formula, which is super convenient. Same thing happened here. Right? So the probability that it is working is going to be what are the chances it's working given that it was working the previous day versus what are the chances that it's working given that it was not working the previous day. You add those up, that's Bayes' formula, version 1, unofficial. That would give you this. Probably that is not working using Bayes' formula, version 1, unofficial, would be that. So this is the probability you're in state 2. On day 2. This guy, by the way, is called another state matrix. This is called S2. Right? So S1 was what we started with. S2, this is the second state matrix. Time flies. Are we out of time already? So, what do you think you would do to figure out what's going on in day 3? You're going to take this die and you're going to multiply that again, right? And ultimately, you should get to this number, although we're missing the 0.99. We're missing a 0.99 here. The fact that it was in state 1 in the first place. But we're going to do that. So, yeah, review your matrix multiplication. It's going to be very important. So we're going to be able to draw chains and then do matrices to figure out what we're going to do.
Failed, which equals like what?
I'll wear whatever you wear.
I doubt it's gonna